Hello, my name is Jai Bhagat and my ID number is 22CS008. So today in this presentation, I am going to explain instruction level parallelism. So this is a powerful technique of instruction level parallelism which maximizes the number of instructions our processor can execute at the same time. That means in one unit time we can execute more than one instruction. So what do we mean by instruction level parallelism? It is a technique that allows multiple instructions to be executed at the same time by a processor. And how does it work? Basically, ILP works by finding independent instructions that can be executed concurrently without altering the output. So let us say we have a chip in which 3 to 4 processors are there and we have 3 instructions to be executed and we want all the 3 instructions to execute at the same time. So the sub processors in on that chip will execute one instructions. So we can say in one unit time more than one instruction is executed. What are the benefits of ILP? It can improve the performance of a processor and reduce the program execution time. And the limitation that it requires complex logic operations which will take more time and generate more heat. Data parallelism. So in data parallelism, we have two aspects, SIMD. SIMD means single instruction, multiple data. So by executing a single instruction, we can work on multiple data elements. And MIMD, that means multiple instructions, multiple data. This is a technique used by processors to execute multiple instructions on multiple data elements simultaneously. Its use case is it is often used in image and signal processing, scientific simulations, and machine learning algorithms. Now we talk about types of ILP. So there are here two types of ILP: data dependency ILP and control dependency ILP. So first we talk about data dependency ILP. Let us say we have three instructions, which is A is equal to B plus D, or let us say S is equal to T plus S. And the third instruction is Q is equal to A plus S. So on a chip, there are three processors. The first two processors will execute the first two instructions. But the third instruction is doing the addition of A and S. So how we will get the data of A and S when they are processing? So there is a data dependency on the processor. This type of ILP occurs when instructions depend on each other's output data. That means if we do not get the output of the previous instructions, we cannot perform the further instructions. Or we can say this is a limitation of instruction level parallelism. Control dependency. This type of ILP arises when the processor must execute one of the several possible paths based on the result of previous calculation. Now, by instruction level parallelism, what performance impact do we have on the processor? So its benefit is improved processor performance and faster execution time of programs. And limitation is it increase complexity of processor and take longer cycle times. Now challenges while exploiting the ILP is dependency between the instructions. As we have talked that in data dependency, if we do not get the outcome of the previous processors, the next instruction will not be performed. It can be understood by pipeline and branch prediction failures. So here in this image, here it is shown a pipeline, 5-stage pipeline in which instructions are fetching, executing memory, and it stores the operand. So we can see that to exploit ILP, we can use this technique that no processor is free here. When one processor is decoding the instruction, in meanwhile time the next instruction will be fetched. So here there is no loss of time. So we can say that in 1 unit time more instructions will be executed. So techniques for exploiting ILP pipelining, as we have talked, instructions are broken down into stages and different instructions can be executed in different stages at the same time. This is like an assembly line for instructions. So this type of pipelining can be seen in superscalar architecture where multiple instructions are issued and executed by multiple functional units in parallel. So no processor is idle here. Every processor works as per the instruction. Out of order execution. Instructions are executed as soon as all their operands are available, regardless of whether the instructions before them have completed. This allows independent instructions to execute out of order. Speculative execution. So in speculative execution, it means that it might execute the instructions, but it actually needs, but it's not sure. Because if it turns out to have executed unnecessary instructions, it will just discard them. So there are two types of dependencies in ILP: data dependency and control dependency. We have already discussed data dependency. Let us say control dependency. The outcome of a calculation determines which instruction is to be executed next, and instructions cannot be executed until the outcome of previous instruction is known. That means here there is all control on the previous instruction. In meanwhile time, if the outcome of previous instruction is not known, the next instruction cannot be performed. Pipeline hazards and branch prediction. Pipeline hazards: instructions in the pipeline that cannot be executed due to dependency conflicts, structural conflicts, or resource conflicts. Branch prediction: the processor predicts the outcome of a branch and speculatively executes the following instructions. But if the prediction is wrong, the pipeline stalls and lost cycles are wasted. Exploiting ILP. We have seen how we can exploit the ILP. Clever processors designs like superscalar architecture, they use this type of technique which reduce the pipeline hazards and improve the performance. What are the challenges of ILP? There are various challenges of ILP. First one is loop dependencies. Instructions that depend on the results of previous iterations of a loop. Let us say our instruction is executing in a loop. So there will be a loop dependency in which the next instruction, how it can be executed, it will totally depend on the previous instruction in previous iteration of the loop. Branch dependency: instructions that depend on the outcome of previous branch. Resource constraints: processors have limited resources such as execution units and cache, which can lead to contention and competition for resources. What can be the future of ILP? Future of ILP in multi-core processors. So ILP is seen offered in multi-core processors like dual-core processors, Intel Peptine, and many other dual-core processors. Processors are now being designed with multiple cores to enable increased parallelism at the thread and task levels. Vector processing is also used. Processors are being designed with longer vectors to enable increased parallelism at data level. Hardware and software co-design. It is also used in hardware and software co-design. That means the hardware and software designers are collaborating more closely to optimize both the hardware and software for instruction level parallelism. So we conclude that this ILP is a powerful technique for enhancing performance, speeding up the computation in modern world, and improving efficiency in modern computing systems. By understanding how they work, their advantages and best practices, developers can unlock the full potential of parallel processing. Thanks for watching.